is that if you've bothered to look at the slides, if we go earlier on in the slideshow, I know it's a little bit ways back. Dang, where'd it go? I must have cut and pasted by accident. Removed it from the slideshow. Oh, there it is. Oh, son of that. Look at that. There's the answers. Oh, so if you looked at the slideshow, there it was. You had the answers. You could have just written down the answers. Oh, that would have been nice.
Yeah, for that one. You got that right.
Because the answers were there, they're honest, maybe.
Okay, so let's actually go through and solve this. So I think I may have heard somebody else already say something, that I said that this was going to be the start of today's class, which means all you had to do was go home and do it. Write it down.
Let's go back to the recording.
And then come back in. And then come back in and write down what your work was, right? Okay. So I'm trying to help you out here so you can get your quiz score points up. We are over our total of 10 quizzes, I believe, which means all you're trying to do now is make up points. So if you have low scores on other quizzes, if you get better scores, you'll start getting the lowest quiz score dropped. Okay? So that'll start helping out. So, oxidation states. What does our oxidation state apply to? Okay. The loss and gain of electrons is how the oxidation state changes. But before we know how it changes, we have to know what it is. What does the oxidation state apply to? I know we did it fast, but we did talk about it. The atom. A single atom is what our oxidation state applies to. So that means when you look at an equation, you have to define the oxidation state for every atom. Okay? So in the first set, well, actually, I guess before that, do you guys want to see this one solved or the second one?
That one.
This one. I'm not doing them all. So, take a look at our first unit. Okay? So now we don't care about anything else. That's the only thing in that unit I need to evaluate it. How many, or what is the oxidation state for copper? Is that one we are required to have memorized? No, which means I don't know what it is. It's X. How many coppers are there? Okay. What's the next element in that unit? In that unit?
That's it.
That's it. There is nothing. Okay. That then has to equal what? The overall charge. Where's the overall charge specified for that unit? Top right corner. What do we have written up there? 0, which means 0. Our oxidation state for copper is 0. Okay. We got to get a little bit more specific than that. That is the oxidation state for copper in the reactant. And why do we have to specify in the reactant? What happens to the copper in the product? Take a look at that unit. In that unit, what's the oxidation number for copper? We don't know it. How many coppers are there? Which equals our overall charge specified in upper right-hand corner. The oxidation number, as you astutely jumped to, was +2. Okay. Did the oxidation state change?
Yes.
Yes. What does that mean? A redox reaction occurred. Now we can go through and define what happened to the copper. As we transition from copper in the reactant to copper in the product, what changed? We lost 2 electrons, which means it was oxidation, or it was oxidized. Okay. If we now want to add in our annoying agents, we can say that that species was the reducing agent. We could also refer to it as and these are some extra terms that you might see pop up, the reductant. Okay, and I just recently saw, teaching a different class this morning, shoot, now I forgot what it was because this really doesn't look right. The reduce, yeah, it must have been something else. This reducizer doesn't look right. Okay. But we've at least got reductant and reducing agent. Okay. So what happened then to the other species? Okay. If we've defined that copper is being oxidized, then we already know that the other one is being reduced. Let's prove it. Okay. To prove it, we need to go through the same thing that we just went through and did with the other units. Okay. What is the first element in that now unit of nitrate? Nitrogen. Do we know the oxidation number for nitrogen? No. So it is X. Sorry, the computer's freaking out. X. How many nitrogens are there? 1. Plus the oxidation state for the next element, which is -2. Okay. How do we know it's -2? That is one of our rules for oxidation states. Okay. You need to know that oxygen is a -2. Times what? Why 3? There's 3 oxygens. What does this have to equal? -1, because upper right-hand corner says a -1. Okay? We can then go through and solve, and you should end up getting that x equals... Way to jump out of there. A lot of people will go through and write 5. When dealing with oxidation and reduction, you'll notice that I will never just leave a number hanging like that. I will specify the charge. We'll write that as a +5. Not critically necessary, but it helps kind of accent the fact that it is positive and not negative. Okay. What happened on the other side? We go through and do the same work. We don't know the oxidation number for our nitrogen. How many nitrogens? 1. Plus the oxidation number for oxygen. -2 times 2, which equals 0. We go through and solve, and we find that x equals +4. What happened to the oxidation state? Okay, it gained an electron. For those of you that are being really good at seeing that. Okay, we could also say that that number was reduced, meaning that that species was reduced, which would then be the oxidizing agent. Okay, or the oxidant, and this is where I got the iser from. The oxidizer. That one's actually true. It is oxidizer. That's legit. Okay. Yeah, maybe reducer. That might be why it didn't show up, because people are like, that just sounds weird. Okay. Kind of makes sense? Okay, can I clear all that?
Yes.
It is cleared. Now on to balancing. Which one do you want to balance?
First one, bottom one.
You guys had to say opposite things. I'm actually going to say the first one we're not going to work through because the first one is relatively straightforward. Why is the first one straightforward?
Because you just have to put a 2 the copper nitrate and then a 2
Okay. The first one is straightforward as far as balancing. That follows our same balancing rules that we've seen before. There's nothing new or fancy behind that. Okay. Nothing particularly crazy. The second one gets a little bit trickier. And it becomes trickier because in our rules we start with, do the elements balance? Well, how many aluminums on the left?
1,
Aluminums on the right? 1. Copper's on the left?
1,
Copper's on the right? 1. Everything looks balanced.
not the charge.
Okay. If we evaluate the charge, do our charges balance? On the left-hand side of the equation, what is our overall charge? +2, and on the right-hand side, +3. So it does not balance. Okay. We have destroyed matter in there. What matter did we destroy? A single electron. That's why we became more positive. Okay. So we can't do that. So we need to go through and come up with a way to balance this. And because we don't have the counter ions like we did in the first example, to help us see how to balance that, we now have to go through a different method, and this is the half reaction method. So what we're going to do is look at our equation and try to group similar terms across the reaction. So for instance, what would I group aluminum with? How about I group it with aluminum? Pretty straightforward. Copper? Okay. So I want to split those equations out so that I can look at them a little bit cleaner. Just because I'm in the blue color, we'll start with copper plus 2 going to copper with what oxidation state? 0. Okay. That is drawing, yes. We can also write underneath it aluminum going to aluminum plus 3. Okay. And our goal is to now deal with those individual equations so that when we add them up, we can get our official balanced equation and everything stacks out appropriately. Okay. So let's focus on the copper one. On the left-hand side, we have a plus 2. On the right-hand side, we have 0. Okay? Charges don't balance. To balance the charge, I will add electrons. Okay, we can't remove electrons. We can only add them. But now the question is, where do I add them? Okay. Everybody said to the left, so I'm going to add to the right. Mainly because I would be wrong. So let's add them to the left. What happens to the charge? I have plus 2 versus negative 1. Did I get closer to balancing the charge or further? I got further away. So that means my assumption of putting the electrons on the right-hand side of the equation was wrong. Okay, so I should have listened to what you had to say. A horrible listener. Okay, so let's go through and now switch it up and do what you guys suggested. And I will add an electron to that side of the equation. And now what's my charge? Plus 1. And because you guys told me to do it, of course you're right. So on the right-hand side of the equation, I have 0. So it didn't balance. Okay. Once we've put one electron on, that gets us the idea of are we getting closer or further. If we're getting closer, it just means we aren't done yet. So what can you do? Add another one. Okay. Now what happened? Now it's balanced. Do we really want to write electron plus copper plus 2? What do we want to do to simplify that? 2 electrons. We'll do the same thing with our aluminum. Okay. Since we've already done the copper one, the aluminum should in theory become easier. Okay. By putting the electrons into our aluminum, remember, our electrons must cancel. If I've already put electrons on the reactant side, where do they need to show up in the case of the aluminum? They have to show up on the product side. So let's take a swing at it and say, well, I want it to cancel. Let's put in 2 electrons. This way my electrons cancel, right? What do you mean? 2 electrons does not equal 2 electrons? Okay, we'll address that. We're just trying to get our charges or our electrons to cancel out first. Okay, but now let's check and make sure that we balance that equation properly. What is the charge on the reactant side of our aluminum equation? What is the charge on the product side? Plus 1. Did we balance it yet? No. So we must balance that equation. We will do so by doing what? Adding a 3rd electron. And I now have my equation balanced. Correct? Okay. Now the trick is that I will now put these 2 equations back together. And in the process of putting them back together, what has to happen to the electrons? They must cancel out. If they're on opposite sides of the equation, the same sign, we can cancel them. Do they evenly cancel? No. I have 2 electrons on one side, 3 electrons on the other. I can do my operations of math. I can subtract 2 from both sides, and I do not get, or I get electrons left over. So it doesn't balance properly. Okay, so I now need to adjust my equations to ensure that when I balance my electrons out, they cancel. So I have to find a common value or common number between 3 and 2. What is the smallest common number between 2 and 3? 6. How do I get 2 to become 6? Multiply by 3. So I'll multiply that 2 by 3, and I get 6. Right? How did I get 6, though? Okay. Does that make chemical sense? How did it become 6?
You need to have 3.
I ran the reaction 3 times, which means there are 3 copper plus 2s and
2.
3 coppers. Not 2, remember we multiplied everything by 3.
I was talking about the
Fair enough. We moved the bottom equation. Okay, we're trying to get that 3 to become a 6. How do we do that? We'll run that bottom reaction twice. Okay? So our aluminum becomes 2 aluminum and 2 aluminum plus 3, and the very end becomes 6 electrons. What happens when I then add those equations to each other? I have something that is similar on both sides, so I will subtract them from both sides to simplify. My electrons will cancel on each side of the equation, and I will be left with 3 copper plus 2 plus 2 aluminum goes to 3 copper plus 2 aluminum plus 3. Right? A couple people are staring at it like, I don't believe you. All right, what do you not believe?
I believe it. It's just dumb.
Unfortunately, I don't know how to respond to it just being dumb. Okay? What we're trying to do is just balance out the pieces. That's all it is. Okay? How can we get those pieces to align? And we're using some kind of mathematic principles from algebra to go through and do this. Okay? As our last check, the whole point of this was to make sure we had a balanced equation. So that means all of the rules we've learned for balancing equations had better results in this being a balanced equation. Otherwise, it didn't work. So how many coppers do we have on the left?
3.
And on the right? How many aluminums do we have on the left? And on the right? What is the charge on the right-hand side of the equation?
6.
Okay. Our copper on the right-hand side has 0 charge. The aluminum, sorry, I just noticed that A. Oh, that can give me you can point that out. So there's our aluminum. Is that what the confused faces were?
Yeah. I
Oh,
don't want to mess up your plug.
okay. I appreciate that. So our copper contributes 0 charge. Each aluminum contributes plus 3, but there are 2 aluminums, which means the charge on the right is plus 6. Charge on the left? Plus 6. Does our charge also balance? What does that mean? The equation is balanced. We can now go through and answer a variety of questions about that equation. Okay. Number 1 being balance the equation. We could say sum of the coefficients. One of the very first answers that you would see in a multiple choice exam would have been 4. Because if we just look at the numbers and say, oh, the elements are balanced across it, we just say it's 4, right? 1 in front of each. Okay. Until we recognize that we also have to balance out the charge. If we have to balance out the charge, our sum of the coefficients becomes 10, 5 on each side of the equation. Okay? Questions about that? Okay, so then let's look at the very last question there. How many electrons were transferred in the course of this reaction? To get the reaction to occur for our copper plus 2, what did it have to do? It had to accept 6 electrons. What did the aluminum have to do? What did the aluminum have to do? Get rid of 6 electrons. How many electrons were transferred? 6. I'm really happy to hear that. Nobody said 12. For those of you thinking 12, 12, yes, is 6 plus 6. Okay? But we have to reference where the electrons are coming and going to. There are 6 electrons released into the solution, those same 6 electrons are absorbed. That means only 6 electrons were transferred in the course of the reaction. Does that make sense?
Yep.
Okay. Yes, that's a little bit tricky to deal with, but hopefully you've got it.
So you're saying it's not 12 because we only dealt with 6 electrons?
Yes.
Okay. You just said that.
In a more blunt way, but yes. Questions about that? Okay, so guess what we finished now? We've pretty much finished all of chemistry. And all those can of worms that was thrown at you, we're done with all the can of worms. Now we're dealing with looking at our equations and moles and doing all of those conversions that you guys have been spending the last, hopefully, 2 weeks practicing on dealing with how we convert grams and moles between each other, because we now need to introduce how do we convert the grams of one substance into the grams of an entirely different substance. Okay? If you don't know how to deal with grams and moles, all of those conversions are going to become meaningless. Okay? So does that mean we need a deep breath here and a breather before we initiate into this?
Yes, please.
Okay, so take your hot minute. I'll accept that. Well, I don't know. We'll see if you define it as easy. So one last thing that we need to address. We have one more reaction type that you may see pop up. Your textbook kind of indirectly talks about it. It does follow through on the context coming from your redox chapter. Combustion. In general, your rule of thumb for combustion is an organic material. Anybody know the definition of an organic material? Contains carbon. That's pretty much it. Okay. So an organic material reacting with oxygen gas. You might go, well, isn't that going to give me all sorts of crazy things? Because there's lots of different organic materials. True. Okay. But as long as we have just carbon and hydrogen, our products will always be carbon dioxide and water. Okay. It'll make your calculations, our balancing process, a lot easier to deal with. Let's see, I forget. Do I have an example? I do have one. Okay, so let's pretend I didn't just advance and show you that. And say we're going to take butane, C4H10. You're not expected to know that name, so don't freak out. Okay. Take C4H10, and I want to do a combustion reaction with it. Okay. So take an attempt right now. Spend a hot second to go through, predict the reaction, okay, and then try and balance the equation. We're going to look at our hydrogen. How many hydrogens are on the left? How many hydrogens on the right? 2. So what do we need to do? We need a 5 there. And we would now have 10, right? And now our oxygen. Patience. How many oxygens on the left? 2. How many oxygens on the right? 4 and 2 gets us 8 and 8 and 5, 13. How do I get 2 equal to 13? We could go through and use decimals, but then we have fractional molecules. Are we allowed to have fractional molecules? No. Okay, and this is where this one becomes tricky. So if you encounter this, what we can do is take a look at our oxygen, or whatever species wasn't balancing properly. What is its subscript? 2. So what I'm going to do is go through and say, okay, you didn't balance out nicely. I'm going to double everything.
He's going to double everything, he said.
4 times 2 would become
8,
5 times 2 becomes
10.
okay. This screwed up all of that balancing work I've already gone through and done. So let's reset all those. Say that again?
Why did you pick 8 and 10 again?
So it's a good thing I erased that. What numbers do we have in front of the CO2 and the H2O? We had 4 and 5. When I multiply everything through by 2, 4 times 2, there's my 8. 5 times 2 is 10. Okay. And yes, that may look ugly and be, oh, I didn't want to have to do that. Sometimes it sucks, you just got to deal with it. Okay. Carbon, how many carbons? 8 and 8. So our numbers may have increased, but because we'd already gone through and balanced the carbons and adjusted everything upwards, it should still balance out our carbons okay. How many hydrogens? 20. I know, that's a massive number, but we got to deal with it. And on the left, or right, I think I got my left and rights confused, but it's 20 on each side. Okay, oxygens. We have 4 and 8 times 2 is 10 times 1 is, we get 26. Okay. And now you might be going, well, 4 and 26 isn't much better. So let's take a moment here. Let's ignore that 2 for a moment. Just pause. Can I get 2 to become 26? How do I do that?
Can you do that over again?
Okay. So we'll rewind that also because I think I didn't actually record at the beginning of that. So, so I do need to work through it again just to make sure we're recorded all the way through. Okay. Questions about what's immediately up there? Okay.
Would this balance out fully?
Yeah. If you go through and check, it will balance out fully. So let's go ahead and start again. Carbon. How many carbons on each side? 4 on the left and 1 on the right. That doesn't balance, so what do we need? I need to put a 4 in front. Okay. Now what do I balance? Hydrogen. How many hydrogens on the left? Hydrogens on the right. 2. How do I make the 2 become 5? Or sorry, 10.
Multiply by 5.
I need to multiply by 5, so I'll put a 5 out front, and this becomes 10. Okay. We're still solid all the way up to here, right? Okay. Oxygen. On the left and on the right. 4 and 2 gets us 8. Plus the 5 with our 1 gets us 5, which gets us a total of 13, right? And 2 can't go into 13 evenly, and we need to have whole numbers go through and deal with this. So what we'll do is we'll go back to our equation and we'll look at our oxygen that's being problematic. The oxygen is being problematic right here. Okay. And we're noticing that it is O2. So what we're going to do is take advantage of that 2 and multiply everything in our equation by 2. Okay. What happens when we take C4H10 and multiply by 2?
You get 2.
Just put 2 in the front. What happens with our oxygen?
You get 2O2.
2 in the front. 8
4
times 2
8.
We should just
Ah.
re-record this whole thing.
gets us 8. 2 times our 5
10.
gets us to 10. There's a question.
You didn't put the 2 in front of the C4H10 the first time you did it.
I thought I did.
Yeah, you did. You did.
I did.
And he erased it, or like you'll see soon.
No, you erased it.
It was-
I erased the O2. Yeah. So if we now go back to our equation, because we just went through and said, well, that sucked, let me just scale everything upwards. Okay? Which is fine. If it doesn't balance nicely, scale everything upwards and try again. If it still doesn't balance, what can you do? Scale everything upward again. Okay? What you will encounter in this class is you'll only run into the scaling it upwards once. You'll only go up to multiplying everything by 2. Okay? In 151, there is the potential for scaling it upward by 8. Okay? And that comes from sulfur. Sulfur in one of its elemental forms is S8. Okay? And that's the only reason you would scale up. So our issue comes down to things in their elemental species. Why do we typically only scale up by 2? Most of our molecules are diatomic. We don't really have triatomic or higher elements to worry about. Okay? Now let's check our work. How many carbons on the left? Carbons on the right. Hydrogens on the left. Hydrogens on the right. Oxygens on the left. 4. Oxygens on the right. 26. Okay. When our numbers didn't match before, we tried to come up with some way to scale it. Okay. We have O2 in our formula. So one of the things that we can do is kind of ignore that we put that 2 in there. How can I make 2 oxygens equal to 26? I need 13 of them. So I would need an extra 9 oxygens. Okay? Which takes our, did I do that math right? Okay. No, we would actually need an extra 9 sets, okay, to get us up to our 13 oxygens, which then means 26 on the left. How many on the right? 26. And it's balanced. Okay. What's that? You can just ignore the number that you've put in front of the oxygen after you've doubled it if you would like. And that can make it easier to go through and balance.
So the answer is actually.
So if we asked for the sum of the coefficients, yeah, I can't do that in my head either. We get 15 and 18. We get 33 for our answer for our sum of the coefficients. At most, one question like this. You're still responsible for being able to acknowledge that it is a combustion reaction. How do we know it's a combustion reaction? We're looking at an organic material with oxygen gas producing carbon dioxide and water. Follow the pattern. Okay? This just happens to be one of the more advanced balancing issues that can pop up. I know you're happy with that.
Well, I'm just looking at it, and I mean, I could see an easier way, but I don't think I'd get the same answer if I did it that way.
If you don't get the same answer, you're not doing it right.
Like, okay, so when you started with the oxygen, on the product side, you had 13, right? Like, let's just say you didn't multiply everything, you just looked at the reactant, or the product side, and you had the 13 oxygen, the O2.
Okay.
The oxygen. You could just multiply the first one by 2, and then the next one's by 2 if you knew that that was 4 and 10. That's basically, or 4 and 5, basically what we did, and then we'd have to do a long thing. 13 would be right there. Like,
Add 2, carry the 4, multiply by 6. Yeah, that's all we did. Yeah, you're right. What you are doing is effectively the same thing that you've processed through in your head that we just walked through. Okay. So there are a variety of methods of looking at this. I personally don't use this way. I use a slightly different way, but it involves fractions, and that freaks people out even worse than you are freaked out right now. Okay. So I've tried to avoid the fractions. Okay. So if you can see it and set up the patterning where you get the same answer, you're fine.
okay.
Yeah. Okay. So that's it. Chapter 8 are mole conversions. Okay. So conversion factors. So this is really chapter 8 and chapter 9 now. You're slinking together a whole bunch of conversion factors. In unit 1, we talked about measurements. Okay. How did we convert our measurements? How did we go from grams to pounds?
Dimensional analysis.
We used dimensional analysis. And what did we need to convert between grams and pounds? A conversion factor, which was 454 grams equals 1 pound. You all memorized that one, right?
Totally.
Okay. Does the rest of the class really want to accept that you're supposed to have that memorized? Okay. So did you memorize them? No. Why did you not memorize that number? Because I told you I would give it to you. Okay? Don't spend time memorizing stuff if I've given it to you. How do you know it's been given to you? It's on the front of the exam. Okay? referencing the exam. How many people have read the exam cover to cover when they first got it? Oh, two or three people. Okay. Did anybody read the direction that says the most common multiple choice answer is?
Yeah.
Yeah? Has anybody actually gone through and checked that?
Sometimes.
It's actually true. 30% of your answers follow that, which gets you a good 5 to 10% bonus over just raw guessing. Okay? The reason you read directions is because there's useful information there. Okay? Don't spend your time memorizing stuff that isn't useful. Okay? So if you don't know what to memorize or not, look at the cover of the exam because you have a practice one. Look at that and say, oh, I don't need to memorize that. He's telling me that. I don't have this information given to me. What should you do with it? Then you need to memorize it. Okay? So our conversion factors with measurements. English to metric are either given to you on the front of the exam, okay, or they're not asked about. Okay? What if it's within a system? Say within the metric system. How do we convert from milliliters to liters? Memorizing what? Yes. The conversion factor of what milli meant. That allows you to do the conversion factor. So back in Unit 1, when I said you need to know what that little m means, this is why. Okay? The analysis of how you set up those problems in Unit 1 is the same thing that we'll then do when we're trying to convert the number of atoms, okay, or the number of molecules, or the number of moles, or even our molar mass. They're all following off the same thing. You have to be able to now look for and find that information. So when we look at our number of atoms, where's our number of atom information found? There, okay, I'll kind of accept that. And you get a little bit more descriptive in reading what the slide says. In the formula, how many magnesium atoms are in magnesium chloride? You now have a conversion factor. 1 magnesium atom equals 1 magnesium chloride. You can now use that as a conversion factor in your dimensional analysis. That information is given to you. Okay? Maybe it's not given to you in a formula. Maybe it's given to you in a name. In which case, nomenclature. Chapter 6. That's why you needed to know your nomenclature, because it comes back. Okay? The next big part that we've looked at is we spent all of Chapter 7 looking at balanced equations. Why look at balanced equations? What are they allowing us to convert? If I give you 1 tin plus 2, how much tin plus 4 can I make? 1. Using the coefficients from the balanced equation. I again have a conversion factor that allows me to relate that. Okay? We could make it even fancier, and I can say, if I give you 1 tin plus 2, how many iron atoms are required to react? How many iron 3s are required to react? 2. Okay, what if I give you 1 mole of iron atoms?
2 iron.
It is now 2 moles of iron. Okay? The mole is just a scaling factor for a number of them. What if I said 1 gram of iron? Be careful. We can't use grams in our equation. When we look at the balanced equation, does it tell us anything about mass? No, it's only the number of the atom. It's the number of those pieces. There's no mass information. So how can I get mass involved? I need to use my molar mass, where I can get either grams per atom or grams per mole. Where was that information found? The periodic table. Okay? The periodic table has a lot of information in it. That's a big conversion factor. So it's a question of going back to it and finding it. The last big one, the number of moles. You can get them from our formulas and molecules, which we've already talked about. The other places are atoms and molecules. And sometimes, if we get really mean, we can go through and use
Units.
Avogadro's number to allow us to do that conversion. So, another way to go through and look at it is putting it all into kind of a line. We can start with atoms or molecules of any species, and I can convert that to AMUs. How do I convert to AMUs? A periodic table allows me to convert. To go from AMUs to grams, how can I do that? I need a conversion factor. That conversion factor is AMUs to grams. What if I don't want to go through AMUs and I want to go through instead moles? I can go through a mole conversion. Okay? And that's dealing with our grams and moles. Can we go from grams to moles?
Yes.
What's that conversion factor found? Periodic table. Can I go from the moles of one species to the moles of another species?
Sure.
The only way I can change is when I'm showing how to change. How do we know how to change from one species to another? How many cars can you build with 4 bicycles? How many cars can you build with 4 wheels?
One car.
1 car. How do you know that?
Because the car is
You know how to build a car using an equation. Okay? Those are something you can visually see. What we're writing out and spent chapter 7 doing is coming up with equations, ways to build cars. Okay? They're just incredibly tiny cars. What are the pieces that we need to add to it? Okay? Once we have moles of B, we can then convert to grams of B. How do we go from moles of B to grams of B? Periodic table. Except now instead of looking at A, we look at B. Okay? So it's a question of where those conversion factors are found and how you manipulate them. So let's do some manipulation. What is the mass in grams of 2.55 times 10 to the 23rd atoms of lead? So to set you up, what do we want to start with? It's the same thing we've started with every time we've started a conversion question. What do we want? What do we want? So I heard 2 answers, atoms of lead and mass of grams. We're looking for the mass in grams of lead. Atoms is not part of it. Atoms is a separate unit from grams. What did we start with? Atoms of lead. In our ideal situation, what would we hope happens? Actually, our super ideal situation, what would we hope happens?
We just go straight to the grams.
Atoms of lead is grams of lead. They are the same thing. Are they the same thing? No. So that's not our super ideal situation. What's the next most ideal situation? I can cancel atoms of lead and get grams of lead. Is there a conversion factor that relates grams and atoms that you know? 1.661 10 to the minus 24?
Yeah.
Grams is
That's AMU.
1 AMU. Is AMU atoms of lead?
No.
No. So that's not a bad idea for a conversion factor, but we're not in AMUs yet. Okay? So now the question is, how do we move through the next sequence of calculations? You need to go through and convert minimally atoms of lead to something. The goal being to eventually get us to grams of lead. Okay? There are at least 2 pathways to get there. I'll give you a couple minutes here to give it a shot. Don't shout it all out real quietly at once. We need to convert it. It needs to disappear from our equation, right? So where does atoms of lead need to show up in my conversion factor? On the bottom. What can I convert atoms of lead into? Okay, AMUs is a perfectly valid conversion. Okay? Where do I find information about the AMUs per atom of lead? Periodic table. What number do I end up using? There it is. 207.2 AMUs in one atom of lead. So this is useful. I'm now starting to propagate closer because AMUs are a unit of weight. Let's get a little bit more scientific. Mass. And grams are a unit of mass. So we're starting to get closer. But is AMUs grams? No. So we're closer but not quite all the way there. Which then means what do we need to do? We need to convert AMUs into something else. So what has to happen in our next conversion factor? AMUs must be on the bottom. Well, AMU is a measurement of mass, and grams are a measurement of mass. So we're doing a mass-mass conversion. Okay? We're doing a weird, goofy mass-mass conversion. What do we do with weird, goofy mass-mass conversions? We could straight up avoid them, or we could say, please, Mike, be nice. Let's look at the front of the exam and hope I see a conversion that relates grams and AMUs. And when we look at the front of the exam, what do we end up finding? The conversion factor. 1.661 times 10 to the 24th grams is 1 AMU. What happens? Atoms of lead cancel. AMUs cancel. And we have what for our unit? Grams of lead. There's our answer. Okay. This does assume that you have this conversion factor, either memorized or on the exam. I think it is on the exam, but I'm not positive. What's that? Oh, sorry, yeah, it's negative 24. I said negative 24, didn't I?
No.
Oh. Okay. Sorry, it's negative 24. Okay. Is there another way we could go through and do this conversion? The answer is yes. Yes, there is. 2.55 times 10 to the, where's the number? 23rd atoms of lead. Our atoms of lead will still need to be on the denominator. Can I convert atoms into anything other than mass? I can convert them into moles of lead. What is the conversion factor between atoms and moles? 6.022 tens to the 23rd. Atoms is 1 mole. Whoops.
So we have to
0.022 times 10 to the 23rd. Are you required to know Avogadro's number? Yes. Yes. Avogadro's number is one that you are required to know. Remember, other chemists throw parties on mole day. If they decide to throw parties, we at least have to memorize it. Okay? So we're now in units of moles of lead. Is that our answer?
I'm curious how you know that, but
What, do they throw parties?
yeah.
Do they have moles of avocado?
Let's get through this one question, guys. Moles of lead needs to show up in our denominator. Question?
I'm sorry, this is kind of, maybe I'm dumb. I can't tell. Is that a 2.7, 2.3, 2.2?
6.022 times 10 to the 23rd is our Avogadro's number.
Appreciate it. Thank you.
Or you're not done then.
No, it's tiny writing. Okay. What do we want moles to be converted to? Grams of what? Of lead. Where do we find information about the relationship between mass and moles? The periodic table. The number is 207.2 grams per 1 mole. And what ends up happening? We would end up with grams of lead. Are those calculations the same? We're using the same numbers, right? We've got a 1.66 and a 6.022. Those certainly don't look like the same number. What is the relationship between those two numbers? For those of us math inclined might know the key word. They are reciprocals. If you take 1 divided by 6.022 times 10 to the 23rd, what do you get? 1.66 times 10 to the negative 24th. Okay? They are opposites of each other.
Oh, so they like.
So they give us the same result, which is why the periodic table is awesome, because we can use it as AMUs or we can use it as grams. Okay? Depending on what we're trying to work with. And depending on what you see as a valid way to get through this. Okay? And this is where our conversions will become tricky. As we continue to practice these on Tuesday, what's going to end up happening is you will look at it and be like, isn't there another way to do it? Yes, there will be another way to do it. Okay? And it's going to come down to how you see your conversion factors. Always use a conversion factor. Don't start shuffling different terms. Okay? So you need to make sure that you have the units nailed down for each of your numbers. And we